This tutorial will start with an explanation of the application functionality, and second, I will run a pre-built version of this application and explain the output, and third, I will step by step write and explain the code using an Eclipse IDE. Now, we want to use the genetic algorithm in order to discover a formula that applies the addition, subtraction, multiplication, division, and modulo arithmetic operators to a collection of tuples and produce a calculated result that equals this expected result. And in this example, one possible formula to discover after going through a number of generations is this formula in postfix notations, and it would be written this way in regular notations. This is the pre-built application, so if I go ahead and run it, we went from generation 0 to generation 5, and we ended up discovering this formula in postfix notations, and it would be written this way in regular notations. And in each generation we have a population of 6 groups of expressions, and each group of expressions has 3 expressions, and for this group we have a fitness of 2, since the calculated result is equal to the expected result for those 2 expressions, and it's different here. And we have the groups sorted by fitness, and this represents it's a table representation of this group of expressions. So we have those 2 expressions have the expected result is equal to the calculated result. And here we have all the expected results are equal to their calculated results. Next, I went ahead and created a new project, and it has a driver class with a main method, and this class would be driving the application, and an expression class, and a group class representing a group of expressions, and a population class representing a population of groups of expressions, and a genetic algorithm class. And this is where we will have the logic for selection, crossover, mutation, and elitism. Now in the driver class, let's define the training data as a 2-dimensional array, string array. So we have the operands and the expected result, and we here have 3 expressions. And we will define the operators that can be used in this application here in the expression class. So we can use addition, subtraction, multiplication, division, and modulo operators. And the operands in the expressions can have 1 or more digits. So let me define the number of digits, and we will be able to pick that up using the string tokenizer and then next token and the length. So we end up picking up this for now, so we end up with 1, but it's possible that it would be 2 digits or more. And an expression could be a number, meaning it would be a leaf expression. So we'll have this Boolean is leaf, or it could be made up of a left expression, a right expression, and an operator. And an expression or a class, an instance of the expression class could have an expected result, a calculated result, and a string postfix expression, and a number of operands. And that would be, in this case, 6 operands, since we have 6 here and here and here. And we will have get methods for the expected result, the calculated result, and the postfix expression. And we will use the number of operands and the number of digits. So number of digits from here and number of operands, in order to find out what the operator index is and what the crossover point is. And I will have set methods for the expected result and the calculated result. And in case we have a leaf expression, meaning a number expression, we will have this constructor that takes in that number as a string, and we will set the isLeaf flag to true, and the postfix expression would be that leaf expression, and we will have a calculate result method that would calculate the result and set the calculated result here. So let's define that method here. So for now it's returning 0, and I'll be adding the logic later on. And in case it is a non-leaf expression, we will be using this constructor that takes in a right expression, a left expression, and an operator as a string, and for convenience a number of operands. And we set those here. And for the postfix expression, that would be the left expression string value with a space plus the right expression string value with a space and then the operator. And same as here, the calculated result would be what's returned from the calculate result method. And the toString method would return the string value of the postfix expression. And I need 2 methods that would return the postfix formula and the regular formula that would be discovered. So we will have those 2 methods, get postfix formula and get regular formula. So in both those 2 methods, we will use space to pick up the tokens in the postfix expression, and I will use a while loop to go through the tokens, and if that token is an arithmetic operator, then I will append that token, that operator, plus space to the string buffer that we defined over here. Otherwise, we will append x and an increasing value of the I counter plus space. So it would be x1, x2, x3, etc. And we end up returning the string value of that string buffer. And for the regular formula, we do the same thing. We go through the different tokens with a while loop, and if that token is an arithmetic operators, then we do stack.pop and put it in this right, and another stack.pop, put it in left, and then we push onto the stack parentheses opening and closing, and then the string value of left, and then the token, and space, and the string value of right. Otherwise we will push onto the stack x1, x2, x3, etc. And what would be returned as a regular formula would be the value of stack.pop. And finally, let's go ahead and put the logic in the calculate result method. So if we have a leaf, then the double that is returned, so the return value would be the postfix expression, so that number, and we return that number. Otherwise, if we have a leaf, then the value of left calculated result would be left expression dot calculate result, and the value for right calculated result would be right expression dot calculate result. And here we do an if else statements going through, and if we have addition as an arithmetic operator, then we perform that addition and we put that value in return value. And same thing for subtraction, multiplication, division, and modulo operator. So this should do it for this class. Next, the group class will have an array list of expressions and a get method that returns that array list. And a group will have a fitness and a get fitness method that goes through all the expressions in the array list, and for each expression where the expected result is equal to the calculated result, it adds 1 to the fitness, and it ends up returning that fitness. And we will have a generate expression method that takes a string expression and an expected result as a string and a number of operands for convenience, and returns an expression instance. So we will use the space to pick up all the tokens in the passed in string expression, and here we are going through those tokens, and if the token is an arithmetic operator, then we handle it here. Otherwise, if it is a number, we simply push onto the stack. So we define the stack here of expressions. So we push onto the stack a new expression passing in the token, the number, as a string. So if it is an arithmetic operator, then we do stack.pop, and that would be the left expression, and we do another stack.pop, and that would be the right expression, and then we push onto the stack a new expression passing in the left expression, the right expression, the token, and for convenience the number of operands. And here we define the return expression, so that return expression would be what's returned from stack.pop, and we set the expected result and the calculated result for that return expression. And the calculated result is set by calling the calculate result method on that expression instance, the return expression, and we end up returning that return expression. So this should do it for this class. Next, let's go to the genetic algorithm class and define some constants. So the mutation rate, the crossover rate, and we'll set them to 0.5 for the purpose of this tutorial. And the tournament selection size will be two groups, and the population size, so we would have 6 groups in a population, and the number of elite groups will be 1. Now going to the population class, we'll have an array list of groups, and the size of that array list will be the population size, and we'll have a get method that returns those groups, and a sort by fitness method that sorts groups in this array list by fitness. So it's using Java 8, and we will need to randomly generate operators given the number of operands. So we will have this method generate random operators. So the number of operators will be the number of operands minus 1, and we generate this number of operators. So we use math.random and expression.operators.size. So we're using this array list to pick up randomly operators from here. And finally we will have 3 different constructors: a default constructor, and one that takes in another instance of population and use that instance to construct and return a new instance of population, and a third one that takes in the population size and the number of operands, and goes through each one of the training data, adding the operators to those operands. So this is what we are doing here. So we do group.generate expression, which would return an expression instance, and we add it to this group that we instantiate here, and we end up adding that group to this group's array list. And this would be the operands, space, and then the operators, and this is the expected result. So from here, and for convenience the number of operands. So this should do it for this class. Next, let's go to the genetic algorithm class, and since this would be very similar to the previous tutorial, I'm gonna go very fast on this class. So we'll have a crossover group method and a mutate group method. So this one performs crossover on a group. So we're passing group 1 and group 2, and for convenience the number of operands, and it performs crossover on those two groups and return a crossover group. And for mutate group, we are passing it a group, and for convenience a number of operands, and it does mutation on that group and returns it as a mutated group. And we will be using tournament selection. So this is the method that does that. We are passing it the full population, and for convenience the number of operands, and it instantiates a tournament population and returns that randomly selected tournament population after sorting it by fitness. And in this case we'll have two groups in this population, since the tournament selection size is 2. Now those two methods, crossover group and the mutate group methods, will end up being called by crossover population and by mutate population. And the crossover population makes calls to the select tournament population 2 times in order to pick up group 1 and group 2 that are used when we call crossover group. And finally we will have this public evolve method that takes in a population and for convenience a number of operands, and end up calling the crossover population, and what's returned from that, it calls the mutate population on it, and end up returning that population. So this should do it for this class. Next, let's go to the driver class, and let's define a lower calculated result bound and an upper calculated result bound. And we will have this method that prints the heading for each generation. And 3 formatting methods. So format string expression, and format expected result, and one for formatting the calculated result. And another print method, so print population, and this will print the population below the heading per generation. And we will have a print group of expressions as a table, and now going to main. I will instantiate a new driver and pick up the number of operands and instantiate a new population. So this would be generation 0, and I will print that generation and print the group of expressions as a table. So the fittest group in that generation will be printed as a table. And next, let me instantiate a genetic algorithm, and I'll go through that population, checking the fitness of the fittest group in that generation, and if not all the expected results are equal to the training result, then we keep doing the while loop. And here we will evolve the population and then print that population and print the group of expressions as a table of the fittest group in that generation. And when all the expected results are equal to the calculated result in the fittest group in a generation, then we exit that while loop and find out what the formula that we discovered in postfix notations and as a regular notation formula. So this should do it. Next, let's go ahead and test run this application. So we just did 2 generations and we discovered this formula in postfix notation and written this way in regular notations. So here all the expected results and calculated result are equal. And we have all the groups sorted by fitness in each generation. So this group has the highest fitness. And let's go ahead and try it with a different training data. So here we will have 4 different expressions. I went to generation 35 and from generation 0 here we have fitness of 4, so all the expected results are equal to the calculated results, and we discovered this formula in postfix notation written this way in regular notations. And let's also try one with here we have 1 digits for each one of the operands. So let's have 3 digits for each one of the operands and see if it can handle that. So here we go. So we discovered this formula written this way in regular notations, and all the expected result are equal to the calculated result here. So we went to generation 9 from generation 0.